Hello, everyone, and welcome to today's Crunch seminar. Today we have two talks. The first speaker is John Kruze. John Kruze IV is an independent physical AI researcher and the developer of G2G physics engine and the Zero Trust physics framework. His research focuses on the intersection of discrete differential geometry, symplectic integration, and bare metal edge runtimes. Originally inspired by decentralized coordination dynamics in biological networks, John's current work is dedicated to developing zero dependency physical grounding layers that enable machines to safely interact with and support biological life. With that, John, we welcome you to the seminar and you may start when you're ready.
Awesome. Thank you, Professor Allen and Nazanin, for setting this up. There, I'd just like to say that I do welcome questions during the presentation because the evolution of this work has happened through conversation and continues to happen through conversation. And that's not just a reference to the MCP native AI process. It's also like as the work gets introduced to new ecosystems, I often learn new ways that it can support those ecosystems. One of the big pieces is like the origin story of how I got here. And it was in December of this last year, NASA lost a spacecraft called Maven. And I thought that was fascinating. I was like, oh, I wonder what's happening. And I started modeling that spacecraft and modeling Mars. And I had already done a lot of Mars EDL with the idea that if I'm running simulations, that the data itself should have like invariants in it and opportunities for me to continue to like, learn. And so that design constraint of the dark window is one of the most important parts of the work because when it comes to uh, cloud connection, reliance on servers that aren't local, if machines are going to support humanity or really importantly, military people, because I am an Army veteran, these machines need to be able to like function in environments that don't support that type of signal. And if we're going to do things in the deep ocean, if we're going to do things in deep space, if we're going to have physical agents working on challenges such as nuclear waste or cleaning the ocean. I care a lot about that. They're going to have to be able to function without being connected to these servers sometimes, and that was demonstrated by Maven. The reason Maven had a big challenge was the positioning of the sun relative to Earth and Mars, and that's where the term dark window came for me. Is that was what I was trying to solve, and the way that I did that, I'm going to jump to the last slide for a second, was this is the bottom layer is the essentially the fabric that the agent exists in during a simulation. So that's the mental model that I had or have, is that in order for Kid Cosmo, so I use Quen, a local agent. That's it works very well on my MacBook. In order for that agent to reason about, for example, the Maven situation, it would have to exist in those physical restraints. And that's where I really got into the modeling of, I call them bodies in experiencing forces, because in my mind, I don't see a very big difference between a submarine in the ocean and a ship in the sky or in space. It is a physical thing with dimensions, experiencing forces that are measurable and oftentimes predictable. It's uh, because the solar system itself is mechanical, uh, in my mind. So that's the original design constraint for what's here is the dark window. before I did that, I was very, very, very obsessed. And we're going to get to this thing here in just a second with modeling biology. So I have a background in clinical pharmacy that happens to fit in here. I was in the army and I did like IVs, chemotherapy, like a lot of things where there were multiple checks and balances with people's lives at stake. So like a mismeasurement could hurt people, especially with ICU care. And I spent a lot of time inside of clean rooms with masks on my face, having to use alcohol because like one microorganism landing in the space of the thing that I'm working on can cause real harm. And that's really represented in the way that I approach the development. Everything here is I'm looking at failure modes, and I use cryptography to have the system attest to itself. And everything I've done, essentially, I use every frontier model to review the math recursively, and that also leads to learning. So that gets us to symmetry preserving compilers, grounding machine embodiment via on-die symplectic observers. All of that work led me to essentially terabytes of data around Mars EDL, ocean, nuclear reactors, hypersonic missiles, F-35s, S-15s. I think this stuff is really cool and fun. And after modeling all of those things, I ended up at this. I ended up with a on die. It moves at 1,000 hertz. It can do more. Like there was a point where I got it up to like 186,000 using super minimal power and modeling in seconds. That generally only works for like signal propagation, mycelial networks, and biological um, types of modeling where I get those extreme rates. So when it comes to, so there's a big, this is the comparison I started talking about, is when it comes to high level neural policies, VLAs, world models, and there are a few other words there. The just the rate itself makes it so that it's impossible to track certain dynamics on a physical system. And that's where the system comes into play. It's not a replacement. That's important. I have like no conception of replacing these models or replacing GPUs. My personal design strategy is I refuse to use a GPU because I'm pushing for efficiency and very like I'm really interested in how systems function again when there's no help. And so that's what I designed for. And all of you already are likely more experienced when it comes to the development of neural policies. And so I imagine you recognize these latency dynamics. And a lot of the time, a 20 to 200 millisecond latency gap sounds like nothing, right? But on a physical system, that is enough time for catastrophic failure. That's enough time for the titanium joint in a humanoid robot to overextend and break. That's enough time for a surgical robot to like miss a very tiny data point and push too far and cause damage. And so what the reflex arc is about is maintaining state, because these models are in my mind kind of state machines. When they're given data that shifts their state, and if um, the safety floor is moving at that pace and consistently projecting physical invariants into the neural networks, it supports the neural networks in staying in their lane. And I have one unverifiable experiential claim that I have not determined the appropriate experiments to figure out yet. And that is that I've learned that this system over here on the right, it produces data sets. And in my early time of modeling, my mental model was I want to have the most immaculate high value data sets out there. And I was actually looking at a platform called BitTensor because I know the founder of BitTensor. I'm like, oh man, I'm going to go crush his game. Like in a competitive sense, like I'm going to go be good at that. And that just led to everything I do being cryptography native. And so the unverifiable claim or experience, this is something I've seen, this is something I've experienced, it's very fascinating, and I don't have the ability to test it, is that running these, doing these runs where, I'm going to use Mars EDL for an example. Let's say I run 10,000 runs of the local model trying to land on Mars. And it dies a whole bunch of the time. That modeling creates data that has physics invariants in it and also demonstrates thermodynamic edge cases. Like you can't go past here, you will die. And what I saw and what I've experienced and what has been really profound, again, that I cannot claim, I don't know how to measure, is when I put these data structures into the frontier models, it fundamentally shifts the way that they behave in a way that's mind-boggling. And I tested it across numerous of them, like even going as far as Perplexity, which is a model I don't have any use or relation to. I just wanted to take the data and the zero knowledge proofs and put them into the model and see what it would do. And it really, really causes fascinating changes. And I put that in, I'm saying that now because I mentioned that the purpose of this reflex arc is to perpetually push those invariants into the context window of the neural network so the neural networks understand the thermodynamic restrictions of physical reality. And these are some, so this is actually like where my heart lives, the thing that I'm showing here now. The direction that I see myself going. I took a turn into robotics, space, etc., because it's a very primary financially viable direction at the moment, as well as I am an Army veteran. And on February 20, whatever, Operation Epic Fury happened. When that happened, in my mind, I'm going, okay, there are a whole bunch of my brothers and sisters who are out there at wartime with systems that I personally don't trust. And so these are things I do on my own time. I'm not like I don't really actively search to collaborate just yet because I've been so focused with the zero trust physics paradigm and like, so working in the physical machines. So I have pathogens. You guys can see these are the equations, these are the invariants that we use to like, do the modeling.
John, we recognize equations and we see the equations, but at least I'm a little bit lost in the connection. So if you can take us through an example, let's say we'll look at this diffusion reaction equation where you have the Fisher term, right? Right. What do you do with that? What can you just give us a case study with that equation of what your research is about? So maybe in a nutshell, we can sort of focusing on that equation, we can see what you're after.
Yeah,
Because
so
you give the
with
high
that
level, and we're not qualified to understand. I don't think we have the background to span across those domains. I'm just
okay.
applied math people.
Okay, yeah, I appreciate that and I welcome questions. And I actually asked my AI to give me some warnings on things that I might do, and my AI told me I might sound like an alien. So to try and stay high level. So very specifically there, it's about modeling a lot to do with modeling the gut. And I had two reasons why I was really fascinated with modeling the gut. The first one is I modeled like a cow's internal system because I was like very interested in regenerative agriculture and climate science. And one of the
Yeah, I mean this is a well-known equation. It's
okay.
called the Fisher reaction term. So it's perfectly okay. But you want to solve it? You want to solve it on the chip? You want to do what do you want to do? Because we know how to do that with pins, with many different methods. But
Yes, yes. So
what do you do that?
my
What?
my
Yeah,
main reason is for studying pathogens in the biological system, and a lot of pathogens move through the gut, and those things are like pretty hard to model like effectively. So that's something I've been working on for over a year, is just modeling the human body for a deeper understanding of how pathogens work in the body, as well as how to support drug and like clinical options for like supporting the human body is a big part of why I'm doing that. And that circles far back to like my pharmacy background, and I just have a lot of interest in cancer specifically. Like I had multiple family members die from cancer, so on my like free time, I study the just human nervous system because like I want to support solving those problems. I wouldn't call myself a medical professional though. That's something I it's part of
but
my
how
heart.
does that, John? How does that relate to the computer science arguments you were doing before with non GPU and so on? I missed that connection. I mean, are you going to solve this to understand the gut with some real
Uh,
data, I suppose, and try to model, find the reaction constant R and so on? But is there a computer science component in here too? That
yeah. So these things are modeled through the same system that I'm presenting on. So the same system that does the cycle to project the invariants to the physicals is the same system I use to work on solving these types of challenges as well.
I
And
see.
yeah, I have this like so like my there's like a professional push on, and that's the physical stuff, and then my personal direction is that like down the road, I know that I'm going to work with like wearables for the human body, and the current technology is not capable of monitoring or measuring a lot of biodynamic activities in the human body. And I'm working on having the software that essentially monitors a robot be able to monitor the human body as well, because I think that like in my opinion, the current pharmaceutical model is very disjointed, and it doesn't treat the human body as a full thermodynamic system. It's a very complex thermodynamic system. So these things here are me modeling it as a thermodynamic system with the intent of having a software that can go onto a wearable that's highly efficient and uses these equations to measure those things and have invariants that can then be projected into an AI model. And then the AI model has um, a much deeper data set of that particular human's metabolic processes than ever before possible.
Okay. Thank you.
Yeah. Yeah. Thank you for the question. I think questions are important again, because this all um, developed through experience and conversations and me meeting with professionals and them telling me what they're experiencing. So this entire slide, we basically just went through exactly what I'm moving towards and what I'm working on is I really care about the natural world, and I don't actually care that much about robots. I want the robots to care about the natural world. Of course, robots don't care, but like I want to like my intent is to support the mechanical systems to support life supporting systems. And that's what this whole slide is about, is that particular system. And yeah, so thank you for that particular question. And that's also what the bottom right one is about too. I have a background in like teaching meditation and breath work and yoga, and I do those things every day. And I do them very specifically because when I was younger, I learned that they affect the somatic system. They affect the way the brain works. They affect the certain neural pathways, especially like yin yoga and certain types of deep breathing. And I personally like I really want to measure that stuff. And like I want to know what happens. I want to have like the most advanced measuring system for what happens when people are consuming like psychedelic mushrooms, because I went really deep into John Hopkins research. I'm a veteran. I've studied PTSD a lot, and I stumbled across John Hopkins Research Institute's research around the front part of the brain, and how those systems relate to PTSD, and how like breath work, meditation, yoga, and even psilocybin. And I've seen some things on ketamine, but I don't know anything about that personally. I don't study that. And so this entire slide is about how do we model the biological systems the same way that I modeled the cyber physical systems. And I find them to be a lot more complex, closed thermodynamic systems. And I would say that I'm not totally complete on building that one. But the one for the machines is complete and running. And yeah. So this is another really interesting. So this is on the computer science part. This is a big part of how I've gotten where I've gotten is systems level programming and cache alignment, as well as zero heap allocation in the memory. And I do most of this model is in Rust. Again, one of my early design constraints was also to not use a GPU and to not do it visually, because I don't need to watch the video while the math is being done. And that was just an initial early thinking. And I have this real fascination with like nuclear power, not in the traditional sense, like not nuclear power plants, but just the humanity evolving kind of the way that we're doing those things. And I got really deep into studying plutonium, and I ended up modeling plutonium, and that led to this ability to model deep time. And at really fascinating like speeds. I recognize that saying that I ran 30,000 trajectories at 17,000 trajectories a second, and like the total runtime was under 2 seconds sounds like kind of insane, because like even for me, as I've started to these throughputs have started to evolve, and I think that's an important thing to say. It's been an evolution. And so I was studying the chip, and I was looking at GPUs, and I'm looking at this particular CPU. And one of the big things that kept sticking in my head is like floating points, and how a a single floating point moving can eventually lead to catastrophic failure because of statistical buildup. And yeah, so this one here is really just about the throughput and having some demonstration of like benchmarking. And one of the questions I asked is, and this is a question that humanity seems to be asking, is what does multiplanetary dynamics look like. And so again, I went back to the question of the dark window, and it's what does the AI, so the AI is on a ship by itself, and we sent it off, we want you to go past Pluto and experience this and experience this and experience this. I started wanting to model that, and modeling over extended periods of time was one of the biggest challenges I personally came across. And it wasn't, I didn't think that my studying of plutonium was going to lead to the relationship to deep time, but that's what happened. And so this is a run I actually did last week, and the idea was to, like, over the course of 100 years, the model, the machine, this one's a humanoid. The machine is going to over time lose maximum power, and that means that over time the maximum, like, strength or ability to move is going to diminish, and there's going to be wear on their joints, etc. So this is me attempting to model that, and a lot of my, like, perspective on modeling is to learn from modeling, not necessarily to model and assume that I, like, am complete. It's a, like, recursive process of uh, condensing complex dynamics into something coherent, and then expanding the coherent shape and continuing to, like, evolve this, because I have no idea. I don't have, like, an endpoint. My goal is to support support humanity, life, Earth, etc. And this is the full stack. And then what this is here is, I have a background with a lot of cryptography. So I've studied a lot of cryptography over the past about 7 or 8 years. We're all part of the same collective information. It became very big, and I've been in business and investing, and so when it blew up, a lot of my peers were involved. I got involved. I like technical things, so I just had to learn. I can't help myself. So I started learning about the blockchain, how it works, why does it do that. And I personally, it just made sense to me that, like, AI and crypto are going to collide into some kind of varying technologies. And I was messing around with that, and I decided that having a decentralized memory, that's just what the last thing is, so you know why it's there. This the core substrate acts independently. So layer 0, 1 do not need these to function. I put Kid Cosmo Engine, which is what runs locally on my computer. If this was to be used specifically in a spacecraft, I have not put this in a spacecraft. If it was to be used by an organization that does spacecrafts, etc., I'm quite certain they would, of course, use their own model. So I use, like, what's accessible to me to demonstrate these things. But of course, Quen's not qualified to fly a spaceship. I can attest to that because I watched it fail over and over again. And then Aegis OS and Spectral One are decentralized ways to store the telemetry from the other layers so that they're perpetually accessible. And again, that's all about maintaining state. So a big part of the way that I think is that these systems that I'm building and have built are designed for state maintenance with the models. And I think I might have talked faster than I did on my earlier runs. Yeah, and so one of the biggest things here as well is that so the zero trust paradigm is about attestation. So a big part of why I have it open source is because I think these things are very important for like the like not just myself. And there's no way that me as an individual am I going to go and influence all of these different categories by myself. Like I'm a deep technical guy. I really enjoy these things, and I know that I'm not going to be the one to go and affect space travel and drones and this and that and biological systems. And just an interesting backstory is some years ago, I invested six figures personally. I raised seven figures personally. And at the time, I wasn't as directly technically capable. And everybody involved in the project lost their money. And the reason the money was lost is because we were in narrative. And because we had an ex-NASA scientist, we just assumed like, cool, we got an ex-NASA scientist. This is the thing we say we're doing. It's going to happen on these timelines, of course. And what I learned from losing is that in hindsight, we didn't have any processes to ensure that we could validate progress. We were in layer five. We were living in narrative. And so that's why I ended up in the zero trust paradigm is I think it's important, including myself, to demonstrate over articulate, especially because a lot of the things that I'm talking about, I honestly don't know how to tell people a lot of the things. Like I'm prone to like literally my AI told me try not to sound like an alien. So that's kind of the whole system. It started with this question, the dark window. If I was an AI on a, I was just imagining like this environment, like what things would an AI need to know when it doesn't have a connection to the cloud, when it doesn't have anything to affect it? And the answer that I came to is that it needs to be able to understand its position in space time. And you don't determine position in space time with cameras. And I know that there are a lot of sensors that don't exist yet for the things that I want to be possible. So that's that. Don't trust, verify. I open source the GitHub. I also have data sets that demonstrate the data structure, and the some of them are 30 something dimensions. So I have those on Hugging Face. And yeah, if you guys are all this is an education and learning paradigm here at the university. So if anybody goes into the GitHub or anything and has questions, I would happily support you guys in experimenting. At my core, I'm a scientist who happens to do engineering.
All right, we'll now open the floor for questions.
Maybe I want to ask this question again. We're looking at the edge stack. Can you and there's all these numbers, 1,000 hertz and so on. Uh, is this a software stack that
Yes,
one can use to solve all these other equations? And
yes.
and would that take less than on a GPU, or it would do exactly like a GPU, or what is the current state of this edge stack?
So the answer to your question is the actual first part of the stack. So this part, the GG core, is all that anyone would need for solving the equations that are mentioned throughout the presentation, as well as more. And the difference between using a GPU and the way that I've approached it is CPU based and it's computational physics. So there's no matrix multiplication in anything that I do. And I'm also not an expert on neural networks necessarily. So I don't develop neural networks or those type of statistical models. It's just not my specialty. And so these equations are integrated on the CPU cores. And actually, this needs to be done on a CPU. I wouldn't know how to do this on a GPU, actually. So yes.
Well, you're doing sampling. John, you're doing sampling, right? So like these trajectories that you talked about earlier. So
Yes.
you're doing some sort of sampling, either since you're doing matrix vector multiply. So GPU is not good for sampling. We know that. CPU is much faster for sampling.
Okay.
So,
So
but are the computational complexity for you, the operations are basically Monte Carlo sampling?
yes. Yeah, large scale Monte Carlo. And it's been a very long and rigorous uh, process to getting it to being this efficient. It took me a lot of time and experimenting to integrate the equations and get it to move at the pace and get things aligned with the CPU registers themselves. And so now at this point, through a lot of effort, all of the equations that I presented and more can be run through just the layer one system. So that's where the primary computer science and things that I presented on is in the layer 0 and 1 parts of it. That's what's on primarily on GitHub, and this is what produces the data sets.
And then what is the middle panel here? It says layer 2 NPU. Not sure what
Yeah,
NPU
okay.
stands for.
So that's a neural processing unit, and I have a MacBook Pro M4, so like it relative to like the hardware I'm using. What this does is it puts I'll tell you the semantic layer what I was thinking. In my head, I'm like, man, I want a local AI to fly a spaceship with MCP tools. How do I do that? That was last year. And that's what Kid Cosmo is. And so Kid Cosmo is a, a it's so that a model can reason through the GG core. And so I wanted to basically the thing everybody's talking about is like, how do I have one of these models like use a robot body and or use these things? And so I started simulating it to just kind of see what would happen because I wanted to understand the tooling, the processing, like the data flows, and like what has to be in the context window of an AI to even understand these things, right? And that's what the layer two is. And so that means that like I don't have the compute and I don't build models right now. So a different model could be put in Quen's place. So that's what the Kid Cosmo engine is I put the infrastructure together so that if the other organizations with more compute and like a desire to test things that aren't like, my personal wheelhouse, they can put their models in there. They can do runs and they can fine tune their own models. So I fine tuned Quen to attempt to fly spaceships. It's not good at it, but I tried. And so that's what the layer two is about, is putting a local model into the physics environments to like, test how it responds as well as fine tune it.
And then the third layer, which said there's is a cryptographic, or it's
Yes.
how does that relate to the previous two now?
Okay. So I mentioned that I was in the military. I follow what the military is doing very diligently. And I presented to the Department of War and I have conversations with some people over at DevCom, because what I'm looking at here is I was asking myself how to solve problems that it's called the Defense Innovation Unit. They basically publish the challenges that the military is facing regularly, and they put it out as procurement, but they describe the problems that the military is facing. And one of the things I wanted to solve was like a decentralized mechanism for treating these agents like they need to be monitored and their decisions need to be stored. And so that's what the Spectra 1 model is it takes the telemetry from the first two layers and it stores it cryptographically on something called the ICP. It's a protocol that is incredibly efficient and low cost. And I don't think that it would be the way that the protocol I use is to demonstrate the possibility. I don't think that it would be the ideal one necessarily. Like a new one would need to be developed for the use case.
Is the memory layer? Is it a memory layer with a code? Is that what you're trying to do
Yes,
here?
yes, that's
Okay.
exactly the intent, is a memory layer, 100%.
Okay. Yeah. Okay. All right. It's very different concepts from what we are used to, but it sounds futuristic. But you already have it.
Yeah. To be fair, there are times where I personally have like a little bit of like kind of like hit my head, like, is this real life? Did I really do that? And I'll even go and like run a test to make myself like feel grounded in what's here. So yeah, thank you. I really appreciate the questions. Again, my intent, a big part of my intent is supporting other people. Like my intent is to be a force multiplier. I don't create content or things like that. Like I'm not very interested in like just being out there. I really want to help deep tech. I really want to support deep tech. I'm especially interested in supporting like science. And at the core of everything, I do believe, and I have really committed my life to this belief, that artificial intelligence and machine learning are going to support humanity with their biggest challenges, and that our next phase is beautiful and we're going in a good direction. And so I'm just doing everything that I can to support that process collectively.
Great. Thank you very much.
Are there any other questions for John? Okay. If not, thank you, John, for the presentation. We'll move on to the second talk of the day.
Thanks for having me.
Thank you for the presentation. Nikita, can you try sharing the screen?
Yes, 1 second.
So the second talk is by Sergey and Nikita. They'll be presenting their work on neural operators with adaptive spectral and low rank representations. Sergey Gatovlin is a lead research scientist at the Social Modeling Lab of the Central Economics and Mathematics Institute at the Russian Academy of Sciences and an information security specialist. He holds a PhD in economics, specializing in mathematical and instrumental methods, and is a graduate of the State University of Management. Nikita Sakovich is a research engineer at the Industrial Programming Laboratory of the Russian Technological University, MIRIA. He is currently a bachelor student in software engineering at the Financial University. We welcome you to the Kruze seminar, and you may start sharing the screen.
Thank you very much. Dear colleagues, good afternoon and good evening to my Moscow friends, and I'm happy to see our whole team online. First of all, let me thank Professor Kaniadakis for this wonderful opportunity to present our research group's work at this world-renowned Kruze seminar at Brown University. And let me thank his team for professional support. We truly admire Professor Kaniadis' work and we follow it closely and always look forward to his new publications. His pioneering research serves as a foundation for our experimental and comparative performance analysis of models, algorithms, and methods, and we strive to develop this area to its full potential. We are deeply grateful for the opportunity to participate in this great academic exchange and hope it lays a groundwork for future collaboration. Our presentation today is focused on hybrid adaptive spectral flow-rank models, and we will cover the mathematical foundations, the underlying algorithm, the software implementation. We show ablation studies and comparative performances analysis. We will demonstrate how our proposed approach overcomes the limitation of existing methods identified during our preliminary desk research for this area of 2026. And for example, one of the major challenges in our view is how to combine complementary representations while maintaining efficiency and grid invariance. Nikita, switch, please. Thank you very much. So we are first time here, and let's get started with a brief introduction of our research group. And our research group goal is twofold. We focus not only on the mathematical and algorithmic foundations, but also on the development and implementation of industrial solutions. For this reason, our teams include representatives from both academic institutions like Central Economics and Mathematics Institute of the Russian Academy of Sciences and the Industrial Programming Laboratory at Russian Technological University. And this allows us, on the one hand, to foster a strong synergy between academic institution and university structure. And on the other hand, it gives us the opportunity to integrate our newly developed approaches directly in the curricula and educational process, thereby training a new research team of young scientists in close alignment with real-world business challenges. Regarding application, our primary focus is cybersecurity issues, some technical and engineering problems, network security, social engineering problem, and this presentation cover as benchmark for our model canonical equation of mathematical physics. We deal with PhD solution approximations. However, we are also actively exploring AI technology for modeling complex socioeconomic systems, artificial societies, and agent-based economics. And we believe that these problems can be achieved by utilizing some neural architectures like neural operators. At the beginning of this year, we have a quite broad discussion at Moscow Academic Economic Forum about some crisis in economic system modeling, specifically the failure of traditional models to adapt to rapid structural changes, where operator learning could become a notable and reasonable logic step in the evolution of approaches. For instance, by offering adaptive dynamic alternative to the time-consuming and costly development of simulation models like agent-based modeling that mainly search for a single line of the future. And we all know that the search for this single line often becomes wrong. And as we deal with decision-making support systems, and this result does not give an appropriate for such type of systems. At this point, I would like to make a brief remark about regarding how my colleagues at Russian mathematical research centers view neural network technologies in general and the application of such technology to scientific machine learning, like PDA solution approximation, like some particular case. Within traditional mathematical circles, the attitude towards neural network analysis remains quite critical. And this is largely due to ongoing debates over the lack of an explicit chain on inference, which is so essential for the exact sciences. And we have one group of my colleagues and friends which deal with classical numerical methods and are not aware about some possibility which give us this architecture like neural operator. We have the second group that is aware about these methods, but consider them insufficiently rigorous from a methodological standpoint. We have some center in computer science, theoretic computer science, which deal with such type of methods and approach, and sometimes give the world quite successful results. However, the attitude are beginning to shift as XAI tools emerge within neural network analysis. And this includes, for example, a couple of simple examples: solve invited loss function minimization problem with regularization, for Lime framework, or utilizing the Shapley value to access the contribution of each feature to the final prediction as shape framework. And we all know, I remind that the Shapley value is widely used in mathematical economics to evaluate the power of players in cooperative game theory. And now the ecosystem of explainable AI expand and consists of dozen mathematical methods, algorithms, and frameworks implemented as ready-to-use libraries, and we observe a noticeable shift in the perception of deep learning methods. Regarding our core research direction for this project, supported by the Russian Science Foundation, we focus primarily on three areas. First, we develop explainable AI architectures based on Kolmogorov-Arnold representation theorem. I remind that this theorem represents multivariate function as a superposition of univariate ones. Second, we design mathematical optimization method and adaptive algorithm, specifically structural AI model compression, like low-bit quantization. And this year we have done the case with incorporating residual entropy. Third, we employ operator learning to accelerate computing and for complex systems modeling. Operator learning direction is quite new for our team. We started to delve into this subject after recognizing and after we feel its potential about 2 years ago, and today, having performed a large number of computational experiments, we can demonstrate some competitive results and potentially promising direction for the development of such type hybrid deep learning architectures. We present our overview of the domain, generalization of existing approaches, a developed model and direction for future work, and of course, limitation for this approach. We welcome constructive criticism and discussion, which will undoubtedly be the general value to us. At this point, I would like to turn the floor over my to my brilliant young colleague, Nikita. He's a research engineer at our laboratory who successfully balances full-time study with active research and professional development, and he will guide us through the details of the proposed method. Nikita, you are welcome.
Yeah. Thank you for inviting us. I appreciate it. So let me start with the core motivation of our work. Sorry. In modern scientific computing, we always need to solve partial differential equations, and P is everywhere. We see them in thermodynamics, we see them in aerodynamics, and they describe continuous physical systems. And traditionally, we use classical numerical solvers to compute them. It may be finite element methods, or finite difference methods, or discrete element methods, and other. And these methods are highly accurate, but and that is their main benefit. But they have a major drawback. They are extremely expensive. They take too much time to compute the mesh and to compute all calculations. So if you want to change just one boundary parameter or change the mesh, you have to rerun everything, and you have to remesh everything from scratch. And before that, this makes real-time control impossible, and multi-query optimization becomes impossible too. So to solve this bottleneck, the machine learning community shifted to surrogate models. These are deep learning approximations, and once trained, they run in milliseconds and not hours like classical solvers. So recently, we saw the rise of neural operators. Standard networks just map vectors to vectors on a fixed grid, but neural operators are different. They learn mappings directly between infinite-dimensional functional spaces, and that means they are completely mesh invariant. So this brings us to the broader landscape of operator learning. Let's formalize what operator learning actually means. Our goal is simple. We want to map an input function space directly to an output function space. The traditional approach fits discrete sensor data into a standard network, but classical architectures like DeepNet do this differently. DeepNet splits the task. It uses branch trunk structure. The branch network processes the input functions at the fixed sensors, and the trunk network processes spatial or temporal coordinates. Then the outputs are combined via an minor product. They give us a continuous prediction, like g of u of y in that equation. Also, we have a Fourier operator, or FNO. FNO works in the frequency domain. It uses integral kernels in the spectral space. There's neural operators at all, and they are kernel-based because of that integral definition. And in that case, FNO uses a Fourier transform. Also, they have VNO that uses value transform and or Laplace transform. There other. So the best feature of neural operators is mesh invariance. If it once trained, it generalizes across different resolutions, and you don't need to retrain them. They once trained and used like a black box after that. Applications are huge. It's fluid dynamics, it inverse problems, it heat transfer, and actually it works everywhere or sometimes. So let's look at the current landscape. The field has evolved dramatically. We moved away from basic DeepNet and FNO, and now we have many specialized networks. Each framework uses a different inductive bias. For example, DeepNet is purely point-wise. FNO is purely global and spectral. There are also graph-based operators and kernel-based models. Graph-based operators used in to predict some simulations like crash tests and aerodynamics in aircraft. So, but recent studies showed a major problem. No single representation is universally optimal. It depends on the PDE family, and like pure spectral model struggles with sharp shocks, purely pointwise model struggles with long-range global structures, and often leads to over-parameterization some kind. So this brings us to our key challenge. How can we combine these complementary views? And after that, how can we do it adaptively within one unified architecture? And how do we keep it parameter efficient and mesh invariant? This exact question is what drives the development of our model. So let's formalize the mathematical problem at all. We want to learn an operator G. It maps an input function of u of x to an output solution function v of x. We do this directly from data, and we do not need explicit knowledge of the equations during inference. It's purely not driven. So at that system of equations, the first is L theta of u of x equals f of x in omega. L theta is a differential operator parameterized by theta. U of x is some unknown solution. And the second one is b theta of u of x equals g of x on delta omega. There b theta is a boundary condition operator. G of x, the other given function, and delta omega is a domain, is a boundary of the domain. The boundary operator b theta may represent various conditions. That may be a Dirichlet, Neyman condition, or a mixed condition. In practice, more often we see a mixed condition in like in more in other physical problems we can see, you know. So to build a robust surrogate model, we have at least three main goals. The first one is to capture both local interactions and global dependencies. Second, to generalize across completely different meshes. And third, to maintain high accuracy without increasing the parameter footprint. So what is the core idea of our work? Instead of relying blindly on just one representation, we can combine multiple views. We propose to learn three complementary representations of the input function. First, a pointwise representation. This focus on local unstructured future interactions. Second, Chebyshev spectral representation. This codes global smooth structure using orthogonal coefficients. Third, a low rank representation. This enforces structural constraints and keep the parameter count low. But simply averaging these branches is not enough. Different physical problems need different features. Therefore, our main contribution, one of our main contribution is an adaptive fusion mechanism. It is purely data-driven and it uses learnable gating networks. The model dynamically decides for each input how much to trust local details versus global spectral shapes. And after that, we can, here's, as you can see, here's a complete blueprint of our architecture. We can trace the data flow from left to right. The input consists of discrete function f and grid points. The spectral grid coordinates go straight into the trunk network. This ensures the final model remains fully continuous and mesh invariant. Actually, it's like a classic DeepNet setup. At the same time, we have the input function f that goes into the three parallel branches. They extract features in isolation. We have the classic MLP branch, we have the Chebyshev branch, and we have the Laurent branch. The fusion of these branches happens hierarchically. We use learnable gate functions. First, the Chebyshev and Laurent branches are fused together. This creates a structured combination. Then the combination is dynamically blended with the unstructured MLP branch. This happens at the second gate. And finally, we take this fused representation and we combine that with the continuous coordinate embedding from the trunk network. For that, we use an element-wise Hadamard product. And the final summation law projects everything into the final predicted solution field. Real few of Y, like that. So let's look deeper into the specific components. There we can start with the Chebyshev spectral branch. This branch explicitly represents the input function within a truncated Chebyshev polynomial bias. Like in the plot, Chebyshev polynomials of the first kind are expression of numerical approximation. They are highly stable and they are non-periodic, so they minimize range phenomenon at the boundaries, and before that, this makes them perfect for boundary value problems. As you can see at the formula, we compute the explicit Chebyshev coefficients, CK. These coefficients give us a very compact summary of the global shape of the function. Next, we take this coefficients vector C of f and CK of f, and we project it into higher latent space. For that, we use a linear lower with White's spec. Then we apply lower normalization, and after that, hyperbolic tangent. So this gives us spec of f. The current issue is simple, I guess. We do not force the network to rebuild global continuity point by point and just feed it the explicit global shape descriptors. And now let's talk about the sort one component. This is the Laurent branch. It is engineered to learn compressed low-dimensional representations of future interactions. We do not map the input through a massive dense matrix. Instead, we approximate that dense transformation. We perform an explicit Laurent factorization. We decompose the mapping into two similar matrices, A and B, and the data passes through an intermediate space R, where the rank R is chosen to be much smaller than input dimension n or hidden dimension h. So as you can see in that formula, this formulation reduce parameter redundancy. It acts as a strong regularization mechanism, and it works because in many physical systems, the solution operator actually lives on a low-dimensional manifold. One important distinction: we are not doing post-trained model compression. We train this low-rank structure from scratch, and it is an explicit inductive bias. It forces the network to retain only the most dominant correlation directions. So, and there, adaptive gating. As I said, different PDs need different feature balances. Smooth diffusion needs global spectral focuses. Sharp convective problems need local point-wise focus. To solve this, we use that driven gating network. It predicts input-dependent weights for each hidden feature coordinate. In the first equation, we have a spec that is a Chebyshev branch and the long embedding HLR. They are fused. We use an accelerate vector alpha of f. Here, alpha of f is computed by concatenating the embeddings and applying an element-wise sigmoid function sigma. Next, we take this combined structured representation Haux. We fuse it with unstructured pointwise embedding HMLP, that the MLP branch. We use a second final gating vector beta of f, and this ensures that more informative branches automatically get higher statistical importance, and everything is optimized jointly end-to-end. There is no manual selection, and the model completely learns what to trust. So let's summarize the entire forward path of the architecture. The three parallel branches process the exact same input function asymmetrically. Each branch extracts a fundamentally different mathematical view of the data. Then the hierarchically adaptive gates unify these views into a single latent vector. This fused representation is paired with the trunk network's continuous coordinate representation. There's two formulas. The first one is just element-wise product, Hadamard product of embeddings of each LoRa, and S is some aggregate function. As you can see in second formula, the aggregate function may be just a sum, and all this formulas, this represents clean multiplicative interaction. So I guess the entire pipeline is fully differentiable, and the model is trained to end-to-end using standard backpropagation. It completely preserves the core mesh invariant benefits of the DeepNet paradigm. So let's review the step-by-step training pipeline. It's pretty simple and classical. There's no something new. First, we initialize our model parameters theta. Then we start our training loop. In each iteration, we sample a mini batch of discrete input functions from generated PD datasets. We also sample the corresponding set of continuous latent points. Then we compute Chebyshev coefficients via our formula, and after that we compute low-rank embeddings. And now we execute the hierarchical gating steps. We calculate the input-dependent sigmoid weights, and after that we simply calculate our aggregation function, and after that we finally compute our empirical loss against the ground truth numerical solutions. So we perform a standard gradient descent step to evaluate all parameters theta. Actually, we used Adam algorithm and Adam V in one of experiments. So the pipeline guarantees fast convergence. Before looking at the empirical results, let's establish the theoretical rigor of our model. We provide a formal universal approximation guarantee. It is right here as several. We consider a continuous operator G. It acts on a complex set of input functions F and the complex spatial domain X. The main mathematical implementation of the theorem is simple. The operator can be decomposed in two distinct components. It's G1 and G2. G1 represents a fin-dimensional highly structured component. It depends on F through a finite number of linear functionals. And the G2 that represent continuous unstructured residual component. So our architecture was designed to explicitly mirror this exact mathematical decomposition. The Chebyshev spectral branch in the lower rank lowers terror to approximate the structure part G1. Meanwhile, the highly expressive multi-branch is perfectly suited to capture the continuous residual variations of G2. The theorem states that for any target accuracy epsilon greater than 0, there exists an operator network configuration of our design that can uniformly approximate this target operator. This provides a theoretical justification for our multi-branch design. So now let's examine our empirical validation. We benchmark our model against standard baseline on, say, canonical PD families. We start with 2D hit equation with prescribed Dirichlet boundary conditions. As you can see, there is the different equation of the hit equation. The input function f encodes the boundary data. The operator must predict the fully diffused interior temperature field U after a fixed time frame. Here, for plots, first one is the boundary condition, then true numerical solution, then predicted solution of the model, and the spatial distribution of the absolute error. The error, as you can see, is distributed very evenly, and it remains especially low across the entire domain and staying mostly under about 0.01. As I guess, this confirms that explicit Chebyshev branch is effective at capturing global and smooth temperature profiles. Then there is stress tested.
Nikita, the three rows are the three samples, right? Three different.
There's the one, yeah. There are three samples of. Here was about 1,000 samples, and there just three of them.
Okay. Yeah, thank you.
Yeah. So there is a Berger's equation in 2 dimensions. There, of course, an equation. Unlike the pure diffusion of the heat equation, Berger's equation introduces a highly nonlinear advection term. And this term drives the formation of incredibly step gradients, shocks, and localized wavefronts. It is challenging benchmark for standard operators.
Nikita, what are you changing here for the Navier-Stokes? Are you changing initial conditions? What is the...
They changed an initial condition, and because that equation is described in like a system in a numerical solution, there velocity, two velocities in space. So it's more challenging because they can be wave fronts, and if we use a small nu in that equation coefficient, there could be some waves,
Yes, but
non-regular.
so the three rows corresponds to what? Different initial conditions or different viscosity?
There are different initial condition, different boundary condition, and different coefficients, of course.
I see. So there are three, you're varying three things at the same time.
We vary
so the input function, you have three input functions, right? That's what you're saying. What goes into the branch? What is the data that go into the branch?
I understand. 1 second. To the branch is, of course, some the input space, the initial condition, and coefficients in trunk net.
Okay. All right.
So in trunk net it's x, y, and t, and in a multi-branch there is just a regular space, and in Chebyshev and Laurent branch is other that space, but changed. So where am I?
Thank you. You can proceed.
Yeah. I just so as you can see, if you look at it as its plots, this specific benchmark highlights why our multi-branch architecture is I guess necessary, because it capturing these sharp step convective fronts. For that requires highly localized and structured high frequency tails. These are provided by the pointwise MLP branch, of course, and stability requires the global inductive bias of the spectral and low rank branches. And the adaptive gates successfully balance this needs. That's low rank at Chebyshev branch. So the source canonical benchmark, it is 2D Laplace equation. It is classic elliptic boundary value problem. In this elliptic system, there is no time evolution, of course, because it's regular. Instead, the solution field or the entire interior domain is completely determined by the continuous Dirichlet boundary conditions. Because this global information propagation is critical, and class change on the boundary edge instantly alters the solution across the entire space. This benchmark showcases the immense value of our Chebyshev spectral branch because elliptic solutions are currently smooth and globally correlated. The Chebyshev coefficients act as a near perfect compact descriptor. This allows the network to solve the boundary value problem with minimal error. Here is quantitative matters collected during our training process. If we look at epoch 1, 0, these initial errors are naturally quite high. They sit at 1.35 for hit or 1.09 for Laplace. But if we look at epoch 100, we observe reduction in prediction error. The hit equation error drops to 0.002 and Laplace drops to 0.03, and as training process further through epochs 200, 300, 400, their matrices continue a steady constant decline. By the final 400 epoch, the hit equation reach an error about 0.001 and Laplace 0.007. Even for the highly nonlinear Burgers equation, the model converges stably. It moves from an initial 0.72 to 0.04. And this constant error reduction across entirely different PT types proves, I guess, that our model delivers a highly stable simulation process. Put these numbers into context, let us look at the actual simulation trajectories. We plot them here against our primary baselines. They're standard DeepNet and FNO. The lower course displays the MC loss on a logarithmic scale or 500 training epochs. There is first on left top is for hit equation, right top for Burgers, and lower left is for Laplace equation. So let's move next. There, the slide presents our extended concept evolution on the held out test set. We report the final test MCA, mean squared error, the relative L2 error, and the relative L infinity error. The matrices are shown as a mean plus minus standard derivation aggregated over multiple independent random seeds. Here the first for hit equation, then Burgers equation, Laplace equation, and you can see the error for all of them aggregated. Next, there it's ablation study. To verify that every single branch is in our architecture is necessary, we conducted a ablation study on the hit equation benchmark. We systematically removed individual components of the model while keeping everything else entirely unchanged. First, we removed a Chebyshev branch. After that, error drops to 5.57 times 10 to minus 4. Then we removed a low rank branch. After that, error was 1.09 times 10 to minus 3. And a third one, we removed adapter gates and just make them min. And there was 506 times 10 to minus 4. And the last one is just MLP only, just don't deepen it. And as we can see, the population study provides that clear empirical proof that all elements must work together as a complete system. And another question for new deploying architectures is hyperparameter, hyperparameter sensitivity, of course. Our model introduces 2K hyperparameters relative to standard DeepNet, the number of Chebyshev polynomial coefficients K, and the rank R of our low-rank range. The table summarizes the sensitivity of our model. The most important takeaway from the data is that the model is highly robust to moderate changes, varying the spectral modes K from 6 all the way to 16 changes the final test MCA by less than a factor of 2. This shows very stable.
Can I ask a question here? Why as you increase the number of Chebyshev terms, the error goes up?
For we vary them
beyond 10. I think beyond 10.
Beyond 10? Well, it's just an empirical question. So we just tested different kind of variants. It's just most interesting for us. Am I understand the question correctly?
If I look at your results,
yeah,
and we look at the K is the number of coefficients, right? Chebyshev. And then R is the low rank. So let's fix low rank to 3. Going from 6 to 10, the error drops, which is good. Going from 10 to 12, the error goes up. And then goes from 12 to 16, and the error still goes up. So is there some sort of an imbalance that causes this?
Yeah, I guess it's about PD family because them was tested on this three PD equations, and I guess the unbalance because of family type. Actually, but the test not actually good. For more correct way, we should vary all these coefficients step by step. First, we need to stay at 3 low rank, and then go with the K charge of coefficients, and step by step go up, of course.
Good evening, colleagues. Can I add one word? Look, all these pictures and these tables is not a scientific result. It's just illustration for our results. So, of course, we need to make choose. No, sorry. Of course, we need to find all variabilities to of these two parameters and find those maximum and or minimum optimal variant. But if we give you all explanation of this, it will be a very large table. So we give you only a small illustration to understand what we mean in this case. Thank you.
You know, of course. I know it's an empirical result, but maybe what's happening here is you provide too much data to the branch, and you need to run longer to fit the data first. Because I saw the number of Nikita, if you don't mind, if you can go back to the training curves, please. You can see that you didn't run it for very long.
Excuse me.
No, the training curves, the plots where you have the training, the history of the convergence. Yeah.
1 second. Yeah.
Yeah. So you run it for 500 epochs. It's not very long time, right? So
yeah, it's.
I can see you can see that it's still going. The loss goes down. So you have to go down for much longer. So maybe because you have incomplete, you exit prematurely, you have incomplete convergence. Maybe that's why the results are not consistent.
Yeah, maybe because of that. If we change epochs to 1000, maybe it be more. We can see more correlation of this.
Because you're processing. I mean, the point is you're processing more information. So you may need a longer.
Yeah, maybe we tested in 1000 epochs, but they then.
My other suggestion, Nikita, would be to use the second order optimizers that we have developed recently. I don't know if you've seen our papers, but those may help also here.
As optimizer.
Second order optimizers, like like
maybe
Newton type optimizers.
yeah, I understand. Maybe second order Newton also like Sophia optimizer.
Look, it's a good idea. Thank you for it. We will trying it, and if you will be interested, we will give you our results.
Yeah, Dimitri, it's not a criticism.
But I guess
it's only a suggestion.
Yeah, but it's interesting suggestion for me too.
Yeah,
yes.
but I excuse me. Yeah, I just guess that Atom Optimizer is SOTA and Atom V is SOTA Optimizer. When maybe the second order optimizing Newton optimizers will be better, but I guess they something else about the results. Maybe I'm wrong. I don't know. But yeah, thank you for question. So can I go further?
Please proceed.
Thank you. Yeah. Let me synthesize our findings and discuss the broader implication for this work. As I guess the core strength of our operator that operator lies in its ability to extract and merge pointwise spectral and low-rank representations. These representations capture entirely complementary mathematical features of an input function. And by using a hierarchical adaptive descent network, the architecture avoids limitations of rigid static designs. The model dynamically and automatically adjusts the importance of structured global patterns versus unstructured local details based on the exact input functions it receives. The data-driven flexibility makes our model entirely well suited for complex heterogeneous datasets. It works perfectly where smooth continuous functions and sharp highly localized shocks coexist. Furthermore, we have shown that campaign multiply explicit inductive biases is vastly more effective than simply increasing the depth of white over a single presentation network like an MLP. Because we rely heavily on LoRa matrices factorization and compact Chebyshev coefficients vectors, the entire architecture remains relatively lightweight. So, about limitations. These limitations point out important areas for refinement. First, our model has so far been evaluated on a relatively limited set of canonical benchmark PGs. While these equations are excellent for control testing and isolating the exact contribution of each branch via ablation, they do not yet fully simulate the extreme multiscale challenges of how to include systems. For example, we have not yet tested full 3D Navier-Stokes simulations and turbulent Kolmogorov flows, or real-world physical weather data like NVIDIA did. Second, our ablation studies indicate that the mathematical contribution of each branch is inherently dependent on a specific problem domain. And third, inducting multiple parallel branches and hierarchical gating equations naturally increase the overall complexity of the network design. This requires more careful tuning of hyperparameters and tuning of network at all. About future work. Our absolute currently well, these current limitations provide us with a very clear existing roadmap for our future search. Our absolute first priority moving forward is an extension of our model to highly regular and structured meshes. Currently, computing Chebyshev coefficients assumes a structured normalized grid. Examining this via generalized coordinate mappings or non-uniform fast Fourier transforms that will allow us to tackle highly complex and real-world engineering geometries. Second, we plan to investigate alternative spectral representations. Well, Chebyshev polynomials phenomenal boundary value problems, exploring spherical harmonics or localized wavelet transforms could yield massive performance boost for climate modeling or astrophysics applications. Third, we aim to design even more sophisticated adaptive fusion mechanism. Finally, we are highly interested in integrating our multi-representation architecture with physical informed training objectives, combine our data-driven multi-branch features with hard physical conservation laws and residual PD loss functions in them. It will ensure our predictions structurally obey the laws physics, like in pins and other. Also, we want to test our model in engineering and economics problems, like to approximate Hank models. It's a heterogeneous agent that to approximate that economical agents in economical world and that help to understand some some variations in the economic laws. So we have introduced our model, Noether. This is a null narrow operator architecture that blends structured pointwise embeddings with structured Chebyshev spectral and low-rank function representations. Our design uses a hierarchical normal observe-getting mechanism to dynamically fuse this complementary information source in a completely input-dependent manner. This ensures flexibility across the entire different PG regimes. On the theoretical side, we have provided a formal universal approximation guarantee. We provided mathematically that our multi-branch formulation is impressive power to model any continuous composable operator. On the practical side, our experiments across heat burgers and Laplace equations demonstrate some performance. So there are reference papers that we published by this topic. And thank you. I'd like to answer a question if you have one.
Thank you for the interesting talk, Nikita and Sergey. We'll now take questions. Maybe I can ask a question. Could you comment a bit more about the low rank representation? How do you choose the matrices A and B? Are they trainable? Or
they're trainable, yeah, of course. The idea that matrices are a neural network weights, and neural network learn to decide which one of these branches is more important at that problem. Sometimes they prefer Chebyshev branch, sometimes they decide to use a low rank, and because there's adaptive mechanism, they are just like a coefficient. And the network, let me one second. Yeah, here. So the alpha, what there's VAUX, it's trainable matrices that depends on Haspec and HL. And after training, they just multiply by HL branch and Haspec branch. And after that, we have AUX that used in a second gate. And after that...
I was asking about the matrices A and B in the low rank representation. I think it was a couple of slides before.
Oh, yeah, low rank.
Yeah, this one. Yeah.
Sorry, I just yeah, they're NB. They of course trainable. That's two lawyers. It can be convolution, but we used linear lawyers.
Oh, so you train them how you train an autoencoder or something. So it's a latent representation.
Yeah, it's two lawyers that apply each to other.
Okay, all right. Thank you.
Thanks, Nikita. I have a question about the structure of your model. Does the order of combining these branches matter? I know that you have 3 branches and 2 gates that combine these branches. So yes, here.
I'm sorry, continue.
Sure, yeah. For example, here you combine Chebyshev and low rank in first gate, and then you add MLP. Do you think would the result change if the, for example, combined MLP and Chebyshev first and then low rank? Or is there any reason for your choice?
That's an excellent question. Actually, it's we tested all combinations, maybe some of these combinations, and this order of combination is just an empirical conclusion, because if we firstly combine MLP and Chebyshev branch, that another network will be work worst. Just maybe it's illogical, but it just was worse than that combination. So it's just an empirical result.
Yes, thank you. And also, I know that you talk about the limitation, but since we have, like the model has 3 branches and 2 gate, do you have any comment about training time? How much more training time or even like GPU memory does it need compared with the DeepNet? Because assume that you have large data set for training, and then if you want to combine these 3 branches, do you have any comment about the memory or like training time?
I'm sorry, I have a connection problem. May I ask you to
Yeah, I can repeat my question. Like,
repeat it?
I was asking that, like here we have 3 branches and 2 gates to combine these branches. Do you have any comment for memory and training time compare with DeepNet, or like how much more training time or memory this model needs compared with DeepNet?
Yeah, it's a little bit slower than classic DeepNet because of that mechanism. Because if we look at complexity time, it's about O of n square, I guess. And classic DeepNet is faster, but not too much.
Yep. Thanks for your presentation.
Thank you.
Have you tried like visualizing the predicted gating functions for different PDEs? For example, like where like you said in the Laplace equation, the global features matter more. So do you see that the gating function gives more importance to the low rank branch than the MLP branch?
Yeah, as in some kind of in one PG family, it's more important to use important gate function, but sometimes Chebyshev branch is more important for understanding the global structure of that equation. And in other PD families, low rank branch helps model understand the local mapping between these functional spaces.
I see. Okay, thank you.
I have a question also. Thank you very much for the presentation. The architecture is of great interest to us, and one could explore many different aspects. One perhaps aspect of great interest would be to see, since you mentioned that all 3 approaches are complementary, we really want to know in these ablation studies that you did, where you removed, for example, the other 2 contributions, how the solution, like the Chebyshev contribution improved what part of the solution compared to vanilla DeepONet. And then the low rank, it may depend on the problem. I understand that, but I think it will be interesting to see indeed that these approaches work synergistically. Okay, and they're indeed complementary. And I think just by looking at not just of course, here the error, that's the overall error, but it's average, right? So the averages sometimes are misleading. It would be nice to subtract the solutions and see the errors and see which parts of the errors are reduced. Is it uniformly everywhere? Or if you look at the solution, the Fourier domain, you may want to see, for example, the Fourier spectrum is better. Imagine that there's a case of very high frequency and we have the problem of spectral bias. Does the Chebyshev contribution correct the spectral bias? That would be a tremendous, accomplishment to answer using these complementary contributions. But I think it's worth checking what extra you get from Chebyshev and low rank compared to the pointwise.
Yeah, thank you. It's an excellent question. Of course, it's interesting, and I guess we research this problem and compare that kernels like an infinite Laplace kernel and wavelet kernel with each other, but in that case we just use the MC mean square error just because it was simple, and of course they need to research more complexly that question.
Yeah, like for example, you see here, the low rank doesn't really do anything, so you don't need to investigate that. But the Chebyshev and the Chebyshev does. So, and then the gates also, the effects of the gates. But I was just talking about the input representations. So the Chebyshev reduces the error significantly. And the question is why?
It's I guess because of family type. In other cases, we tested in burgers or Laplace equation, and then in their cases, low rank was more important than Chebyshev sometimes. Sometimes it's not like here. Sometimes gates is more often to ensure error. And I guess it's more about an initial problem and about an equation and about boundary conditions. Well, sometimes if Dirichlet or Neyman low rank maybe more useful than Chebyshev, sometimes not. So it's just yes, but not a good example in the table. So yeah.
Yeah.
Thank you.
Are there any more questions? Okay. If not, we'll close the session for today. Thank you everyone for joining, and thank you again, Sergey, Nikita, and John for the presentations.
Yeah, thank you for accepting our invitation, Sergey.
George, may I say a couple of words?
Of course.
Thank you very much, and I was not mistaken when I saying that this discussion is the greatest value for us. And we have some consultation during our discussions session, and we very appreciate the suggestion for second order optimizer to expand computational experiments in terms of time training and add such metrics in our models about the specifics of ablation studies, and it's a really good idea, and we are happy to do this. Nikita, could you possibly show the slide before the last slide?
Yeah.
Yes, thank you very much. We have presented today the first paper we published with the same title, and we have another paper we have published letter type, so neural operator using dynamic mode decomposition analysis at the same class of task, and now we are working on long version with all our experiments, and we will happy to present if you want.
Yes. I think that's a good idea. So we'll Alan and Nazan will give you the available slots so we can repeat this and follow up also on the questions.
Thank you very much, George.
Yes, thank you. Thank you. If shortly the DMD neural operator just use dynamic and mode branches like there, but the branches the data goes through the DMD analysis, and then we have dynamic and modes, and then they go through the dynamic branch and modes branch. Oh, yeah. Thank you.
Yeah, George, and we really love your work and are waiting for new research. Thank you very much.
You're welcome. Thank you for joining us today.
Thank you very much.
Bye-bye.
Goodbye.
Thank you.
Thank you.